shaped kind of like a trough with a triangle on one side. Okay, so here's our trough. It's got a pipe coming out of the top of it. And the measurements here are that the depth is 3 meters, the length of the pipe is 2 meters, the width of the triangle is 3 meters, and the length of the trough is 8 meters. And our job in part A is to find the work required to pump the water out of the spout. And the other piece of information that they give us at the beginning is that this tank is full. Okay, and then we also have part B, but in order to answer part B, we're going to have to first set up part A. So, Becky, you asked about this question first, and what were your original thoughts?
I just started using those workforce mass equations, but not what I knew when finding out what I didn't know.
Great. Sounds like a great first step in terms of working on this thing. Okay, so we've got this tank, and one decision that you have to make about this is you need to determine an axis. So where did you choose your axis to start?
0 at the top of the triangle.
So right about here? Okay, great. So our x equals 0 is going to be at the top of the triangle, and then down is going to be positive x? Okay, great. So that's important to make that decision and to make that as a conscious decision. Now, whether you choose to put x equal to 0 at the top of the tank, or the top of the spout, or the bottom of the tank and have it point upwards, all are legitimate ways to set this problem up. It's just going to make the setup look slightly different from your neighbors. So it's important, though, to make that decision because everything is based off of this decision. Okay, so now we want to pick a particular slice. So a generic slice right out of the middle of the tank. So we're going to take our tank, we're going to slice this tank into a bunch of slices, and each one is going to look like a slab. And we want to figure out the work to move or to lift one slab of water. All right, so Becky mentioned, okay, we need some different formulas, things such as work is equal to force times displacement. Well, we can figure out displacement right away. The work to move this slice, well, this slice is at some arbitrary x value on our x-axis, and so the distance we need to move this slice is the distance of x.
Go ahead. I'll ask him.
So we have to move this slab up to the top. That's our distance of x, and then we also need to pull it out of the pipe at the top. So to lift to the top of the tank, we have the distance of x plus an additional 2 meters to pull it out of the pipe at the top. So RD is equal to x plus 2. Jeff?
Or you could have 5 minus x, right?
So thinking... So
if you have it from the top of the pipe.
So if I choose to make... if I choose to do it, and so I'll draw this as a separate option down here. So let's say that I choose x equal to 0 to be at the top of the tank, top of the pipe. Then my slab is still located at a value of x here. And so in fact, in this case, the distance that I'm moving my slab is just the distance of x. You're not happy about that?
Go ahead. I mean, just...
If on the other hand, I had chosen x equal to 0 to be at the bottom, then this And so then the distance that I'm moving my slab, then my distance would be 5 minus x. So those are sort of the 3 different options. So this one down here, these 2 are thought bubbles. There are other options that we can look at. But again, those will make everything else look different as well.
And that's what I was confused as, just choosing your axes and going from there. That's why I couldn't.
And any particular axis that you choose are all valid choices. It's just a matter of, once you choose that, you've got to look at your picture and say, okay, what is the distance I'm actually moving this slab based on the axis that I've chosen?
So since basically our x is equal to 0 is at the top of our 3 meters.
That is the top, this on this version here, or on the one we're actually going to do?
Top one.
On this one up here?
Yeah.
So up here, at the x value is not 3 meters. This 3 meters is the entire height.
Right.
So that when we are looking at the slab that's at the very, very bottom, that's what x is equal to 3. But this slab in the middle here is some x value somewhere between 2 and, somewhere between 0 and 3.
Yeah. All I wanted to get at was since our x is equal to 0, basically
Yes.
at the top of that 3 meters.
Yes.
But we're not. That's just
Right.
where it is. Would we minus R2 from our x over in the
Over here?
displacement? Yeah.
So,
It makes more sense to add it, but
well,
since
think
x
about what
causes
happens is,
down,
if I turn my head upside down,
yeah.
and I think about this height that we are looking at, my top is here and my bottom is here. So my top minus my bottom is going to be x minus a negative 2,
Okay.
which gives us x plus 2. So I mean, that's sort of the top minus bottom version, thinking about that. Any other questions? Okay, so we've got our displacement, which is x plus 2. We now need to look at our force. Our force is mass times acceleration, and acceleration is gravity, so that's 9.8 meters per second squared. Got that. And we still need our mass. And so to calculate the mass, we need density times volume. And density, since we're talking about water, is 1,000 kilograms per cubic meter. And I think that they give us that somewhere earlier on in the problem, or somewhere in the example. Okay, so now all we need is our volume. Are there any questions about anything up to the volume? Other questions? Okay. So now we're looking at the volume. So the volume of our one specific slice right here, this slab that we have, essentially looks like a box. And so if I want to find the volume of this box, it's length times width times height. And so the first thing I want to look at is the little bit. So in other words, the direction that we're slicing. And so my height is a little bit in the x direction. So our height will be dx. All right, the other parts, this one's different than our homework because on the homework we were looking at an upside down pyramid, and so all 4 sides of the slice were changing on that one. On this example, we have this trough, and this distance here along the long length of our trough never changes. That distance is always 8. So no matter which slice we have, our width is going to be 8 meters. And the length is the last one to look at. Are there any questions about height or width?
Wouldn't the length be 8 meters? Yeah. How come the width is 8 meters?
Well, so I labeled, so if I had switched these 2 right here, I just called length and width, I just labeled them.
Oh, okay.
Yeah, so the long side over here is always going to be 8, and then the other side is going to be the one that's going to change. Okay, so that other side that we don't quite have yet, we have to use that similar triangles idea. And so we've got ourselves our triangle, and this is our side view. So we have the end of the trough, and we have our two triangles being our first triangle whose height is 3 and whose width is 3. So 3 is to 3. In the same way, that over here, well, now we need to figure out, this is our L, but we also need this little distance here. Any thoughts on what that distance should be? Okay, Becky, say it a little louder.
3 minus x.
3 minus x. Okay, and this totally makes sense as 3 minus x, because when I look over here, the top part, the part from the slab up to the top of the tank is x, and the whole tank is a depth of 3. And so this bottom part is going to be 3, take away that top x part. So we've got 3 is to 3 in the same way that 3 minus x is to L. Okay, any questions about coming up with this equation right here? Okay, so now I can solve for L, so I've got 1 is equal to 3 minus x over L. Multiply both sides by L, and I have L is equal to 3 minus x. The only reason that we end up with L being exactly the same as the height is because on the bigger triangle, the height to width is a 1-to-1 ratio, and so our height to width on the small triangle will be a 1-to-1 ratio as well. Okay, so now we have all of our information that we need. Okay? So now we need to work it all backwards. So our volume is going to be the length, which is 3 minus x, times the width of 8, times the height of dx. And now I can move back to my mass. And so the mass, which is density times volume, is going to be 1,000 times 3 minus x times 8 times dx. And now we can go from our mass, okay, now we can go back to force. Force is mass times acceleration. And so we've got 1,000 times 3 minus x times 8 times dx times 9.8. That's our force. And then we can go to work, which is force times displacement. So we've got 1,000 times 3 minus x times 8 times dx times 9.8 times the displacement of x plus 2. And so here, after doing all that work, we've written down the work to move one slice of water. Are there any questions on coming up with that one slice? Legitimate expression here. Typically we like the dx at the end, and it's nice to regroup things. So my work for one slice, I've got 1,000 times 8 times 9.8, grouping all the numbers together in the front. And then 3 minus x times x plus 2, and then the dx again. And so our final step now is to say, okay, this is our expression for this slice, but we actually have slices that start down here at the bottom and go all the way up to the top of the tank. So I want to add up the work for all those slices, so we're going to integrate 1,000 times 8 times 9.8 times 3 minus x times x plus 2 times dx. And the slices that I'm looking at, I'm going to be slicing this entire tank up. So I'm going to start here at an x equals 0, and I'm going to slice, 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 until I get to x equal to 3. So we're going to integrate from 0 to 3. All right. Are there any questions on setting up that integral?
I'm a little bit confused with the 2 on top and why that doesn't. I mean, obviously it's not part of the volume as you're going up.
Right.
is it just accounted for in your D?
That's exactly right. That pipe at the top is strictly coming out with every slice that we have. We're lifting it to the top of the tank and then an additional two meters. And that completely comes out here. Now, if you had instead done the labeling where x equal to 0 is at the top of the pipe, then you'd be integrating from x equal to 2 to x equal to 5. And so, whereas our distance would just be x, we'd be accounting for that in the bounds. Okay. All right, other questions?
But in any case, the distance you raise it has to be within the integral.
The distance that you raise it.
Well, you're raising it to get the work.
Yes.
You have to know the distance you're raising that slice.
Yes.
Okay. And when I was looking at this initially, I was thinking you'd have your interval 0 to 5. But it's not 0 to 3, and then the distance that it's raised is in the integral.
That's right. So the distance that the water is raised up to here, that's your x portion.
Right.
And then that 2. So this is
Right.
your distance raised. Now these bounds based on the
Right.
labeling that we've done up
Right.
here,
Right.
those bounds are strictly telling us about
Right.
the water depth.
Right. Right.
Okay, other questions or comments? Okay, so Becky, you had actually asked about part B on this. And so what did you come up with as an answer for part A?
1.06 times 10 to the 6.
1.06 times 10 to the 6, and we're talking about work, and so this is joules.
So all you do is just add your 1008, 9.8, turn it to the front of the integral, and then FOIL the 3 minus x, x plus 2, and then integrate.
That's correct.
And then,
Yeah, take these guys, multiply them together, stick them out in the front,
uh,
FOIL that, integrate.
Yeah.
Okay, so part B. Part B says, suppose the pump breaks down after 4.7 times 10 to the 5th joules of work has been done. What is the depth of the water remaining in the tank? Alright, so suppose the pump breaks down at 4.7 times 10 to the 5th joules of work. What is the depth of the water left in the tank? Okay, so the first comment is here that this is a legitimate question to ask because to move all of the water out of the tank, it requires 1.06 times 10 to the 6 joules, and this is some number that's less than that. So we're imagining here that we're pumping the water out. We're really sad because suddenly the pump is broken. It is over the holiday weekend. You cannot go buy a new one. So we need to figure out how much water is left. Okay, so Becky, do you have any thoughts on this?
Where I'm stuck, I've got it all set up, is I'm guessing it's the lower bound is what we're looking for. But I don't know how to solve for a bound on
Okay, so this seems like this seems very reasonable, a way to think about this. So what's happening is that we're pumping the water out. Now realistically, we're pumping out the water starting with the water on the bottom, the other water is going down. But based on the way that we have our integral set up, let's see what happens if, so to get all of the water out, we have to go from 0 to 3. So let's still start at a value of 0 and see if we can come up with a new upper bound rather than a lower bound on this thing.
Instead of doing all that, can you just take the work, plug it in for our equation, we already have the force, and then solve for the displacement?
This one here?
Yeah.
So that would be very legitimate, except that the work changes depending on what the x value is. And so, yeah, so that's why we have to go with the integral part. So depending on the slice, the work is different. Okay, so that's really what we want to do is take this top number, set an unknown. So, Becky, what's your favorite letter?
Okay.
Okay, great. Okay, so we're going to say that 4.7 times 10 to the 5th is equal to the integral from 0 to k of all of that stuff. 1,000 times 8 times 9.8 times 3 minus x times x plus 2 dx. And so by solving this equation, if we can figure out what k is equal to, what that's going to do is say, okay, we started pumping the water out and we got down to this k value right here, and that's going to say how much water we've pumped out, then we can figure out what the depth is left over. Okay, so I need some help here with this. What is 1,000 times 8 times 9.8? 78,400. So we've got that times the integral from 0 to k. I'm going to go ahead and multiply this, the x values out. So we have 3x plus 6 minus x squared minus 2x, and then a dx at the end. And all that's equal to 4.7 times 10 to the 5th. Okay, so let's go ahead and divide both sides by the 7,840.
None of them were 0.
78,000. If I need an extra 0 on there? Yeah. Great, thank you. Okay. Excellent. Okay, so I need some help with this division on the left side over here. 6. Do I have a second on that number? 6. Okay, 6. It's convenient. That's a nice number that they gave us. Okay, so the integral from 0 to k. I'm going to go ahead and clean up inside the parentheses here. So I've got x plus 6 minus x squared, and then a dx at the end. And my goal is to have this integral be equal to 6. So I'm going to go ahead and integrate. So I've got 1/2 x squared plus 6x minus 1/3 x to the 3rd, evaluated between 0 and k. So first I'll plug in the k, and I've got 1/2 times k squared plus 6 times k minus 1/3 times k to the 3rd. And then I'm going to plug in 0, and I get 0. All right. So now I've got this expression that's got k's all over the place. So if life is awesome, then I can factor this thing. So let's see what happens. I'm going to go ahead and move all my terms to one side. And so I've got 0 is equal to 1/2 k squared plus 6k minus 1/3 k to the 3rd minus 6. And if I'm going to factor this, I better put these things in order from largest to smallest. So I've got negative 1/3 k to the 3rd plus 1/2 k squared plus 6k minus 6. And this does not look that good.
It does say, I think it says in the book just the calculator, because there's a little picture.
Right, so when I look at this, if I didn't have any other information from the textbook, I would look at this and say, I don't know if I really want to factor that, I don't know if I can. So I might try to factor it for a little while, and then I might go to my calculator and say, okay, can I take this expression and can I graph it and figure out where this equation, or I'm sorry, where this function crosses the x-axis? And so I might graph this thing. So if you have your calculator, please graph y equals negative 1/3 k to the 3rd plus 1/2 k squared plus 6k minus 6. Now, I mean, you'll use x's instead of k's. But please go ahead and graph that guy.
Is it necessary to use the k in place of an x? Could you just use x?
Well, so if I use an, so I can use my intersection. So I've got second calc. We'll calculate the 0. We'll pick our left boundary. then our right boundary, you always have to help your calculator on this. And then we're going to take a guess. And it tells us that, I can barely read this up here, y equals 0 and x is equal to 0.972285, which is not something we would have easily found by factoring. Are there any questions about this? Okay, so our final answer over here is that k is approximately 0.9722. That's not quite our answer to the final problem, or final answer to the problem. So what this number is saying is that this is saying that when we look at our side triangle, we are going to start at x equal to 0 and pump water until we get to x is equal to 0.9722. So we're going to pump out all the water from 0 to 0.9722. The actual question that we're asking is, how deep is the water that's left over? So if we want to figure out the depth of our water left over, what do we need to do?
3 minus.
Yeah, do 3 minus the 0.9722. Depth of the water left over is 3 minus 0.9722, which is going to be 2. Need help here.
0278.
Thank you. 0278. Do I have a second on that number? Great. Okay, so our leftover water is at a depth of roughly 2 meters, slightly over. Okay. Are there any questions about that one? Going once, Jeff?
So if we had looked for the lower bound, would have we gotten 2?
So if we had gone, based on the levels that we have here, if we would have gone with the lower bound, because we're starting our slicing at x equals 0 and moving down from the top, we would have wanted to stick with
The lower.
with x equal to 0 being our lower bound and just changing the top bound instead. If, on the other hand, if you had set this up such that x equals 0 at the bottom and positive upwards, then you would have kept your lower bound as x equal to 0, and you would have done a k for the top bound, and then that k would have been your 2 value. So it all depends on how you set up your axis.
Right, okay.
Question about
Yes.
bounds. So definite integral we have a value.
Yes.
Indefinite integral function. Can't we take that answer, whatever it was, it's 4.7, whatever, solve the integral without bounds, give us just a function? At that point, we've got an x to solve for, we've already got an equals. Couldn't we just say, hey, this function of x equals this, just solve for x?
You have to be a little bit careful with that. In this case, you would end up with the same answer because our bottom bound is 0, and when we plug in 0, we get that value as being 0. If we had not started at 0, and if the work for this very bottom slice had not been 0, then there would have been a differing of the constant. Because this integral is in fact giving us the work to move water from a starting level to an ending level. And so getting rid of, or just integrating this, we would have ended up with an expression, but it would have been work starting at 0 and ending at k. And so once you do, wait, ask your last part of the question again, because I think I just got confused.
Because solving for the indefinite integral just gives a function of x, and we
Yes.
already have an answer to that function. That's why I was saying, couldn't we have just not be concerned with the bounds? But I think you were saying, in this case, it's okay, but it's only because we've got 0 to...
Right. In general, what you want, this value is going to be the work for the starting and ending, and this would be the work for, with the x, it would be unclear without any sort of bounds. So this is really a differing of values, so you need that both. Okay, other questions? Okay. So that was was an extensive problem, but that's why there was only 2 out of this section to work on. Okay, so our next subject is going to be section 7.6, which is an introduction to differential equations. So I think maybe we're going to stop a little bit early today on section 7.6, which is an introduction to differential equations. So basically what today is, and maybe part of Wednesday is day 1 of the intro of the differential equations class. So if you are working toward a math major, or if you're an engineer and you plan on doing a math minor, it's very likely that you will be taking differential equations, which you can take after Calc 3. And so I introduced the ideas here. If you never take a differential equations class again, then this is your one day to be able to talk intelligently about what a differential equation is. And if you are going on and taking differential equations, then this is the basic ideas about what that class is all about.
Nice.
Okay. So, we know that if f of x is a function of x, then the derivative of f of x, sometimes called dy over dx, sometimes also called f prime of x, but that derivative is also going to be a function of x. So if I give my first function f of x, if I'm calling that y, so if y equals f of x is a function of x, then the derivative dy over dx is also a function of x. So here's an example where we have y is equal to x squared. So y is some function of x. And so if I take the derivative of e raised to the x squared, well, I have to use the chain rule, and my inside function is x squared, so my derivative is going to be e to the x squared times the derivative of the inside, so times 2x. And oftentimes, I might want to clean this up a little bit. dy over dx is equal to 2x times e to the x squared. That's just sort of the common way to write this. And so we've written the derivative of y is some function of x. Any questions about that derivative? Something that you might notice about that derivative is that e to the x squared showed up as part of the derivative. And notice that e to the x squared is equal to y. So I can replace e to the x squared with a y, and I can write this as dy over dx is equal to 2 times x times y. And so now what I have here is an equation that has x's and y's and a derivative of y with respect to x. And this equation that I have written right here is an example of a differential equation. So a differential equation is an equation that contains an unknown function and one or more of its derivatives. So if you were walking down the street and the equation dy over dx equals 2 times x times y, you're walking down the street and this equation jumps out at you from a dark alley, you immediately know that this is a differential equation because I see a y, which I think of as an unknown function, and I see a derivative of y, and they're connected together in some sort of an equation. And I might have extra terms in there, I might have some numbers thrown in there, I might have some x's thrown in there as well. But my unknown function is y. I mean, you know, when you're walking down the street, we're assuming that you had not originally done this work to come up with dy over dx equals 2 times xy. Okay, so you're walking down the street and you say, okay, here's my differential equation. The goal of solving differential equations is to find a formula for the unknown function. So for the unknown function y equals f of x. And if we can come up with a formula for y is equal to something in terms of x, then we have found a solution to this differential equation. So y equals f of x is called a solution to the differential equation. So differential equations are equations that relate some unknown function with its derivative. And often you might be given a differential equation because you can talk about a real-world scenario where a rate of change is equal to, so in particular with populations, you can talk about how quickly a population is changing in regards to the population itself. And so we'd be relating the population, which might be y, and the population's rate of change. How quickly is that population changing? And that would give us an equation, and our goal would be to come up with a formula which would describe the population at any time t. Okay? And so this is where our differential equations become important. But I'm going to give you one more definition here. Are there any questions so far on these two definitions? What is a differential equation, and what is the goal of solving a differential equation? Okay? So last definition. The order of a differential equation, and I'm going to get tired of writing out the word differential equation, so I'm going to write DE instead. The order of a DE is equal to the order of the highest derivative in the differential equation. So, for example, dy over dx is equal to 2 times xy is a first order differential equation because I only have a first derivative as part of my equation. I might have another differential equation that is d2y over dx squared. That is the second derivative plus 5 times dy over dx squared minus 4y is equal to e to dx. Now, this is a pretty wild differential equation here. We've got a second derivative, d2y over dx squared. I have a first derivative, dy over dx. I meant to make this the third power up here. So 5 times dy over dx, first derivative raised to the third power, and then I have minus 4y equals e to the x. And this is a second order differential equation because the second derivative is the largest order derivative that I have in here. Even though the first derivative is raised to the third power, the order of a differential equation has everything to do with the highest derivative that you have. This is the first derivative, this guy's the second derivative.
So where did 5 plus 5 and 4 come from?
This and this here?
Yeah.
This is a totally made up differential equation.
Oh, okay.
So this is just an example.
Okay.
But when I look at this, I know that it's a second order differential equation because the biggest derivative that I have is the second order, the second derivative. Okay, so what you're looking at right here is a very lucrative business. Okay? Differential equations show up all over the place, whether you want to talk about meteorology, whether you want to talk about biology and populations, whatever you want to talk about, differential equations show up because they are used to model tons of different systems. And the thing is about solving differential equations is that they can be really hard. You can get a PhD for you don't even have to solve a differential equation to get your PhD. You can make progress toward finding a solution to a differential equation. Now, for example, here's a differential equation relating y, which is our unknown function, y's derivative, y's second derivative, as well as y is some function of x. We don't know what the function is yet. And all this stuff is equal to e to the x. If we can come up with a formula that says y is equal to blah-de-blah-de-blah-de in terms of x's, then you've solved this differential equation. And if your differential equation is significantly useful and or significantly challenging, or ideally both, then you can earn a PhD just for making progress towards solving a differential equation. So some differential equations are easier to solve than others. We're not going to do any solving of PhD level differential equations in our introduction to differential equations today. But just keep in mind that there exist differential equations out there that model some really important things that are really hard to solve, but people really want them solved. So you can earn a PhD, you can go off and work in industry, and if you can understand things about the differential equations, then you can help out your company and they'll pay you to do that. Okay, so differential equations are pretty useful.
Take that class.
Okay. So here's an example of a new differential equation. Y prime is equal to negative y squared. So when I look at this differential equation, I can immediately translate y prime into dy over dx. So I have dy over dx is equal to negative y squared. And because the biggest derivative that I see in here is a first derivative, this is a first order differential equation. And our goal is to solve this differential equation, which means find a function, y equals stuff in terms of x, that satisfy this expression. Now, walking down the street, this equation jumps out at you from a dark alley, and you're like, oh, it's a differential equation. I can immediately see that because I see a derivative and I see the mystery function y, and I can tell that it's a first order differential equation because my biggest derivative here is the first derivative. I don't have any tools yet to solve this differential equation, but if you continue to walk and you're walking quickly because you're nervous, down out the second alley pops an equation that says that the solution to this differential equation is y is equal to 1 over x plus c. And so you say, whew, this came down from the clouds, and here's my solution. Let's see if this is a valid solution to this differential equation. So we're going to check to make sure that this solution, which we've just been given, is a solution to this differential equation. Okay, so we're going to check that the solution is correct. So in order to check that a particular solution is correct, what we need to do is check that if we use that solution for the left side and we use that same solution for the right side, that we get the exact same answers on both sides, and that would verify that our solution is correct. So let's start with the left-hand side. The left-hand side is dy over dx. So right now, we know, or we think anyway, that y is equal to 1 over x plus c. And we need to calculate the derivative of 1 over x plus c. So if I want to calculate a derivative of 1 divided by x plus c, c is some constant, I don't know what it is. I have a couple of options here. One option is I can use the quotient rule. The other option is I can rewrite this fraction as x plus c to the negative 1. And then I can use the chain rule. So that my derivative, dy over dx, is equal to negative 1 times x plus c to the negative 2. So derivative of the outside, keeping the inside the same, times the derivative of the inside, and the derivative of this inside is 1. All right, any questions about that derivative? So this is our left-hand side. All right, let's see if we end up on the right-hand side with the exact same thing. So our right-hand side, well, that is negative y squared. Well, our y value is 1 over x plus c, so we end up with negative 1 over x plus c, the quantity squared. All right, and this is our right-hand side. All right, so I'd like you to take a look at the left-hand side and the right-hand side. And then I'd like you to turn to your neighbor and tell your neighbor whether you believe these two sides are equal or not.
For stabbing me?
Both said yes?
Yes.
Okay, can you explain why you say yes?
Well, for the right-hand side, as soon as you actually FOIL that out, you're going to get to the same answer.
In what way? So
if you FOIL, if you get 1 over x plus c times 1 over x plus c, and you actually multiply those two together.
okay. And so we've got 1 on the top, and then an x squared plus 2xc plus c squared on the bottom. Okay.
And then you can kind of FOIL that back in, because you FOILed it out in the first part. Now that you've gotten that from, you FOIL back in that bottom part
Okay.
to just x plus c, and then the bottom part is squared.
Like that?
Yep.
Okay.
Which is the same thing.
All right. So we can multiply this bottom part out. We could also rewrite this initially as negative 1 over, and maybe we don't even need to FOIL it out. We could go directly down to this point down here. Okay, so we have negative 1 over x plus c, the quantity squared, which looks an awful lot like this if we take our negative power here and rewrite it in the denominator, and the times 1 doesn't matter at all. Cool, so yes, these two are in fact the same, which means that that second alley that you walked by and the solution popped out as y equals 1 over x plus c, this is in fact a solution to the differential equation dy over dx is equal to negative y squared. Any questions about that? So far you may be saying, that's great, if you can have the clouds dropping solutions on you, then we can go all day and check those solutions by plugging that solution into the left side of the equation and the right side of the equation and see if they match. But how do we actually find a solution? And I'm not going to answer that question just yet. Okay, so here is our solution, and our solution was y equals 1 over x plus c. Notice that that c value is any arbitrary constant, which actually means that there's an entire family of solutions that all satisfy this differential equation, and they're all different by a constant. One comment though, this is, in one way this is the same plus c that we have when we do an antiderivative, but in another way it's not, because this plus c is showing up in the denominator. It's not showing up as stuff in terms of x and then tack on a constant added on to the end. This constant is actually embedded in the function. So while there is still, each different solution differs by a constant, that constant is not just add on some number at the end. Okay, so how do we deal with that constant? If we actually want to figure out a specific solution for our needs, well then we might say, well suppose that y of 0 is equal to 0.5. So we have some sort of an initial condition or an initial value. So this y of 0 is equal to 0.5. This is called an initial value or an initial condition. So if we know one extra piece of information, one initial value, then we can actually take our solution and figure out what c should be equal to. So we can find what c should be equal to. So we know that y is equal to 1 over x plus c. And we know that when x is equal to 0, y is equal to 0.5. And so we can plug in those values. 0.5 is equal to 1 over 0 plus c. So when x is equal to 0, y is equal to 0.5. That's how I read y of 0 equals 0.5. Now I can solve for c. So I've got 0.5 is equal to 1 over c. I can multiply both sides by c. And I have 0.5 times c is equal to 1. Divide both sides by 0.5. And I end up with c is equal to 2. And so when I'm given an initial value, then I can write down a specific solution. In this case, my specific solution is y is equal to 1 over x plus c, and c is equal to 2. So it's 1 over x plus 2. And this specific solution that I've come up with, this is called the particular solution. So the particular solution for the initial value problem given by y prime is equal to negative y squared with y of 0 is equal to 0.5. Okay, so there's two things going on here. We're given a differential equation, y prime equals negative y squared. The general solution to y prime equals negative y squared, the general solution is y equals 1 over y plus c. And the particular solution, if we're given not only the differential equation, but an initial value as well, then we can actually figure out what that c value should be, and that's called, and the y equals 1 over x plus 2 with a specific c value in there is called a particular solution for the initial value problem, because we're given an initial value. Okay. Any questions or comments about definitions? No?
Is that 1 over x?
Yeah. X plus.
Yeah, this should totally be an x right here. Yeah, that's an x. It's just perfect. Thank you. All right, other questions?
That's minus y to the squared?
Yeah.
Yes.
Okay.
It's kind of hiding up there. Poorly written. So y prime is equal to negative y squared.
It's a negative 2, John.
Okay, other questions? Glad you guys are here to keep me honest about what I'm writing on the board. Okay, so now the next big question is, how the heck do you solve a differential equation? And again, I want to emphasize that the range in which you can solve a differential equation and the challenge of solving a differential equation can go anywhere from what we're going to talk about today up through earning a PhD in math for solving one differential equation. All right, so today we're going to talk about hopefully 2 ideas. We'll certainly talk about 1 idea today. Maybe the second one will be on Wednesday. We'll see. The big question now is, how do we solve differential equations? our first method is a graphical method and involves something called direction fields. Okay, so we're going to learn this by an example. So here's our differential equation. The differential equation is y prime is equal to x plus y. So the derivative of y is equal to this formula over here on the right side, x plus y. All right, our goal is to find a formula for y where y will be some function of x that satisfies this equation. So how do we come up with a formula for y? How do we find a formula for y? All right, well, the thing is that we're going to start out by looking at this graphically and looking at some pictures. And what I see here is an equation where y prime is equal to x plus y. Now, y prime is a derivative of y. I'd like you to think for a second in your head of two other words which mean derivative. So what else does a derivative describe besides just the word derivative?
Slope of a tangent line.
Okay, slope of a tangent line. Any other words? Velocity. So if our y is position based on time, then our derivative is velocity. Okay, rate of change, instantaneous rate of change. So all of these things are things that our derivative represents. So slope, instantaneous rate of change, slope of the tangent line. So just knowing that, I can actually tell a lot about my function y. In particular, I can tell the slope of y at any particular point in the xy plane. So what we're going to draw is we're going to draw something called a slope field. We're going to create an xy plane. And we're going to pick some points in the xy plane. So I'm going to go ahead and mark off values of -2, -1, 0, 1, and 2 on the x-axis. And then 1, 2, 3, and -1 and -2 in the y direction. And I'm going to create a grid for myself. And so at each of these integer values, I'm going to put a point. All right, now we are told that y prime is equal to x plus y. And y prime is the slope of y at a given point. Mark, what's your favorite point that we have drawn up here?
2 and 1, I suppose.
Okay, so 2, 1. So this is Mark's favorite point right up here, 2, 1. And so let's figure out what the slope is at the point 2, 1. I'm going to create a table. I'm going to have my x value. I'm going to have my y value. And then I'm going to have y prime, which we're given is equal to x plus y. So at Mark's favorite point, which is 2, 1, our slope, y prime, is going to be x, which is 2, plus y, which is 1. So our slope is equal to 3. So right around this point, the slope of our function y is a slope of 3. Now, what I'm going to do is I'm going to draw a little mini tangent line that goes right through this point, and that tangent line, well, let's see, here is slope of 1. I need something a little bit steeper than that, so I need something maybe like this. Okay, so the slope of this little mini segment here is roughly a slope of 3. Aaron, what's your favorite point up here?
1 and 1.
1, 1, 1. Okay, so let's take a look at this point 1, 1. So at 1, 1, okay, our slope is going to be 1 plus 1, so y prime will be equal to 2. So here's my slope at 1, 1 with roughly a slope of 2. So slightly less steep than our slope of 3. Okay, so we've now done 2 of these points. Are there any questions on how we're getting these slopes? Okay, well let's look at another one. How about over here at negative 1, 1. So x equals negative 1, y equals 1. Our slope, y prime, is going to be equal to 0. And so I've drawn a slope that's horizontal. Okay, so there's several other points that are all written up here on the board that we have not filled in. And so I'd like you to turn to one of your neighbors, and I'd like you to pair up with one of your neighbors and fill in those slope segments for the rest of these points on here. Are there any questions about what I'm asking you to do?
You want to take
Slope 3, and that's where computers are really nice. And so the very first picture up here is an example of a slope field with all of these grid marks marked in. And so hopefully this picture looks very similar to the one that you have on your paper. And you'll notice that at each grid line, for example, at 0, 0, I cannot see that line segment because our slope at 0, 0 is 0, so it blends in with the x-axis, but there is still one there. And so there's a bunch of other grid lines. Now, right now it kind of looks like a pile of toothpicks that kind of fell on the ground. So I'm not really getting a good sense of what the shape of my function is going to look at. So in order to get a better idea of the shape of my function, I should really start to put some more dots into my picture. So, maybe every half value, and quadruple the number of points that I have, or maybe even every tenth of a value, and make my grid much finer. Now, that suddenly becomes a big pain in the neck if you're doing it by hand, and so instead of doing it by hand, we call on Mathematica, and Mathematica gives us the slope field that you see at the bottom. And so some things that you should check compare between these two. You should compare, for example, at the point 0, 1 on the top as compared to 0, 1 on the bottom. That slope line, although it's shorter in the bottom, should have the same slope. And at 0, 0, your segment should be horizontal on both the top and the bottom. The bottom one just has more points filled in. Okay, so what this picture down here, the slope field, tells us is that you can kind of look at that and imagine these as sort of like wind lines. Imagine yourself sort of falling in there. Suddenly, you can kind of go with the flow of this thing. I mean, I can kind of see the lines going down and kind of going back up again. There's some sort of a shape forming in there. Now, in general, a function passes the vertical line test, and so there's all kinds of slope fields here. Now, how do we choose which of these slope field lines we should look at? Well, that's where our initial condition comes in. And so if I take my equation, my differential equation y prime equals x plus y, along with the initial condition of y of 0 is equal to 1, then I can go ahead and draw a picture of my solution. And I'm going to use the second slope field because it's a little bit better off. Y of 0 is equal to 1 means that when x is equal to 0, y is equal to 1, and I'm going to go ahead and mark that point onto my slope field. Now, these tangent lines, what they're doing is they're giving us a rough shape of our function. And so what I want to do is, as I leave the point 0, 1, I want to follow those slope lines as though they are guiding my curve that I'm looking at. with this pen because it doesn't work. So let's try this. So from this point right here, I'm going to go with the flow and follow these tangent lines. I always want to go in the same direction as the tangent lines. I never want to cross them in a perpendicular way. I can also follow my curve back the other direction. And notice what happens when I get down to here. I do not want to cross a tangent line in any sort of angular way. I want to follow those tangent lines and kind of go with the flow. This is a very loose mathematical class. We want to go with the flow when we're working with these slope fields. And so what we have just created on our slope field is a solution to this differential equation that has the specific initial condition y of 0 is equal to 1. All right, now I don't have a formula for that, but I at least have a picture. Are there any questions on coming up with that picture right there? That is a picture of our particular solution for this initial value problem. Okay. So I'd like you to turn your paper over. And are there any questions before I go? All right, so turn your paper over, and on the back side, we've got a couple of other differential equations. In particular, the specific example on the back of this paper is the differential equation given by x squared plus y squared is equal to y prime plus 1. Now, when I have this equation here, it's not really written in a nice form. I'm going to solve this equation for y prime. And so y prime is equal to x squared plus y squared minus 1. And so I'd like to solve this differential equation graphically. So what I'd be doing is I would create myself a grid. And I'd put some points on it. And for each point, I would create myself a table. My x value, my y value, and then my slope, y prime, which is x squared plus y squared minus 1. Plug in my x value, my y value, get the slope out, draw the slope field, or draw the line segment. And what I would get if I did a lot of those points is I'd get a picture like this. All right, I would encourage you to pick your favorite xy point, plug in your x value, your y value, figure out what the slope should be, and then look on this picture here and see if you agree with the slope line that is given there. Okay. So what we'd like to do is we'd like to sketch the curve, the solution, for the initial value y of 0 is equal to negative 2. All right, so when I look at this, I notice when x equals 0, y is equal to negative 2 is down here towards the bottom. And so I mark my initial point, my initial value, and now from this point, I'm going to go with the flow, both to the right and to the left. Okay, and what do I mean by going with the flow? I mean that my tangent lines are approximating my curve. So here it is. And here it is. Looks like we're getting pretty steep here. And then moving down here, down below. You kind of have to wing it a little bit and go without a safety net when you're going in between the tangent lines, but then once you get to a tangent line, you can kind of go right along with the tangent line. It guides you in the right direction. So here is our solution when y of 0 is equal to negative 2. Are there any questions about drawing that picture? Okay? So I would like you to draw a picture of y of 0 is equal to -1, y of 0 is equal to 0, and y of 0 is equal to +1. So 3 new solutions on this same slope field. But what you'll notice is that the initial condition changes the possible solution very, very much. So depending on what the initial condition is, you can have a function that is always increasing, you can have this function that's going and having this crazy thing going on in the middle, or you can have a function that is a little less crazy like the one on top. So initial conditions can make a very, very big difference in your final solution. Okay, are there any questions about drawing those solutions? These are 4 solutions to this differential equation. 4 different solutions depending on their initial condition. Yeah?
It looks like a lot of them come together,
Yes.
like they meet toward the end, so as they approach maybe infinity, are they the same?
So what's happening is that eventually you want to study differential equations and their end behaviors. Like we want to know what happens to populations as in the long term. And all of these particular solutions have the same end behavior. And so really all the weird stuff is happening around time t equals 0, and then they all become very similar.